This is a lesson on single slit diffraction in a unit on light and optics, where we're looking at interference of light. In previous lessons, I had talked about wave interference, and this wave interference is true with all waves. So you may want to go back and watch that video to highlight that constructive and destructive interference happens at very specific conditions where the path length difference of two different waves are either a whole integer or a half integer of the wavelength. And that relates to superposition of waves. We can just add them together, and when the two peaks line up, we get a larger wave, and when the peak and the trough line up, then we get complete cancellation. And so that's sort of the simple idea of constructive and destructive interference. We also see that there's imperfect wave interference, so not perfectly interfering waves. And I put the water patterns here so that you can kind of imagine this happen. There's a region you can see here where there's a lot of destructive interference. There's a region where there's a lot of bright interference, and in between we're going to have some sort of imperfect interfering wave. And this will be true for light as well. When we look at light, we have to consider where is there perfectly constructive interfering light, perfectly destructive interfering light, and also know that there's going to be a spread in between. There's also these factors affecting waves as they diffract. So I looked at diffraction in a previous lesson, and what we saw there is that the size of the obstacle compared to the wavelength is a significant factor in the diffraction and interference. Any waves that make it into this region will interfere with one another. So the first thing we look at here as we're looking at an obstacle, we're going to send a plane wave, a monochromatic light wave, through a single slit. And so this is what single slit diffraction is. We say we're going to take a hole, we're going to send light through it, and we're going to see what happens on the other side. And as you can expect, the size of that hole really affects the pattern that we see over on some sort of screen. The narrower the slit, the more loss of light that's going to happen. There's more diffraction going on. The diffraction angle isn't as large, and so we're going to get a different pattern than if we have a smaller slit. So that's what we're looking at, is what happens, what does the pattern look like when I send light through a single slit. So the single slit diffraction pattern is shown like this, and you can see down at the bottom, this is a real laser that was sent through a single slit. You can see that there's a central bright fringe. This is what we call the central bright fringe, the wide central fringe. So this is the central fringe right there. And less intense fringes outward. You can see it's really bright in the center, and then as we go outward symmetrically on both sides, it becomes dimmer and it's not as bright. So how we represent that on a graph with intensity, you can think of the axis here as intensity. We have a really bright intensity in the center here, and then out to the side there's less bright. This is a pattern that you see in text representing this pattern here. And so we see there's a central bright fringe, and then each one of these is a dark. Okay, so that is what it looks like when we send a laser through a single slit. And you can imagine if the width of the slit is different, if it's smaller or if it's larger, that would change the width of the central angle and how far that light spreads out. So looking at how far that light spreads out, the diffraction angles of dark fringes. So what we're going to do is say we can locate those dark fringes. I want to locate this dark fringe and I want to locate this dark fringe. We can locate all of those dark fringes. And what we're going to do is rely on what we know about wave interference. We already know that if we're trying to find dark spots, this is destructive interference. And we want the path length difference equal to a half wavelength difference. Some integer value, half integer value of a wavelength difference. Well, when we look at this situation, what we do is to derive this equation, and you won't be responsible for deriving it. I'm just kind of showing you where this comes from, is that we focus on these two waves 3 and 4, And we see that 3 and 4 arrive at a dark spot, and they are not in phase with one another. They are completely out of phase with one another, and they're destructively interfering at that point. As opposed to these two waves from the two ends here, they meet in the center, and they're going to perfectly constructively interfere in the center, and we can see that's where it corresponds to a bright spot. And so you'll get a bright fringe, a bright spot at where there's constructive interference, and a dark spot where there's destructive interference. So how do we figure out the path length difference here? Well, that's not too terrible. What we do is we just draw a little triangle in here. Because we're looking at waves 3 and 4, we're going to look at the path length difference. And they're essentially the same length except right here, this length right here. And it's next to a right angle. And I can enlarge this a little bit here. It looks like this. There's a right angle, and this is half of the width, right? From here to here, this is a half of the width of the slit. There's a right angle. There's an angle theta here, and the path length difference is this side, which you can do trig to see that it's a half w sine theta. That's the side of that triangle right here, is the hypotenuse, which is a half w times sine theta. And so we see the path length difference between 3 and 4 is a half of a wavelength. We would set that equal to destructive interference to find where the dark spot is. So we get a half w sine theta equals m plus a half lambda. And it turns out for any half integer, you're going to have the 2 cancel here and the half cancel here. And so you end up with this equation. And that is the equation that we're going to use in order to locate dark spots for the single slit diffraction pattern. Destructive interference or what we call dark fringes will happen at the angle where we get this relationship going on. Okay, W is the width of the slit. Theta is the angle from the central axis. So there's a central axis in here, and we're going to measure that angle from the central axis. M is the order number of the fringe, which I'll talk about in a second, and lambda is the wavelength. So it's not a terrible equation to use. All of these are pretty easy to identify. The order number of the fringe, what we're going to notice is that M is in here, and it's an integer value. This comes from the fact that we want the path length difference to be half integer values of the wavelengths. So this is how we get these integer values in here. So if I look down here and I call this the central axis, this is where M equals 0 in the center here. As we move outward to this first dark fringe, and you can see that over here, we're going to say this is M equals 1, and down here equals M equals negative 1. Because it's symmetric around that central axis, you'll have a positive angle and you'll have a negative angle, which is fine. We usually only look at the positive values because it is symmetric. We don't necessarily have to do the negative. We just use symmetry with the positive value. So in order to get a non-zero theta value, the lowest M that we can enter in here is 1. That is the order number of that first dark fringe here, M equals 1. And as we move out here, this will be M equals 2, M equals 3, and so forth. So that's how you use the order number. What I'm going to make note specifically for single slits is we do not find the bright spots for single slits. We do know that there is one in the center, but we won't ever worry about where each of the center of those bright fringes are. We won't worry about that. We only locate the dark spots, and often more specifically, we worry about the width of the central bright fringe. How wide is that central bright fringe? That may be like a distance that you're asked for in a problem. So locating fringes, if I wanted to actually find that distance, what I need to do is relate a distance in there, because we're not given any distances here other than the width of this fringe. We need to take that light that's sent through this slit and then project it onto a screen. You can see that there's a screen here. And what they're going to do is tell you or ask you for, depending on the problem, the length the distance from the slit to the screen, which we're calling L. Okay, that's usually called L. And then we also consider the distance up to the dark spot, and that's called delta Y or Y. And we can use simple trig. This is a right angle here. We can use simple trig to see that these two values are related to the angle that we're finding in the equation here. For dark spots for the single slit, we can use it with this trigonometry to relate the distances. So that's how you would solve for that in problems. I picked a pretty straightforward example in order to exemplify the concepts here. There's a single slit here, and it's being projected onto a screen. We're not given any distances, we're just looking at angles. And we can see the intensity on the screen. Here's the M equals 1 dark spots, M equals plus and minus 1 on the top and bottom of the central axis. And we're given a value for M equals 2. I'm going to note that. M equals 2, we're given an angle, 45 degrees to the M equals 2, 1, but we don't know the angle to the M equals 1, 1. And I'm going to caution you, do not just divide by 2. I know that might make sense. We're doing half of the value, but that's not true because the sine value is in here. This is not a linear function, it's a sine function. So there will not be a linear relationship. You cannot just divide by 2. So let's read the problem and see what's going on. It says visible light of wavelength 550 nanometers falls on a single slit and produces its second diffraction minimum, so we're seeing that, at 45 degrees relative to the incident direction of the light. What is the width of the slit? Okay, so it seems like we have enough information to figure out the width of the slit. I'm going to solve this equation for W. W equals m lambda divided by sine theta. I'm going to put in what I know, m equals 2 lambda. I'm going to put in meters. I need to have this in meters. And then I'm going to divide by sine of the angle, which is 45, sine 45. So very simply and directly, I can solve for the width of this single slit, and I get 1.5556 times 10 to the negative 6th meters. This I would simply recommend representing in micrometers, 1.56 micrometers. So that's how wide that slit is 1.56 micrometers. So pretty tiny. The part B asks, at what angle is the first minimum produced? So again, don't just divide by 2. We're going to have to figure out what the new angle is. I'm going to solve this equation for sine theta. Sine theta 1 equals m1 lambda divided by w. So I'll take the inverse sine on both sides and plug in the values for what I know. M equals 1, lambda is still 550 times 10 to the negative 9th. And then the width I just found up here, I'll put in the more exact value, 1.556 times 10 to the negative 6th. And when I run that all through my calculator, this angle for theta 1 is 20.7 degrees. Okay, so again, it's not half, it's a little bit less than half. And so it's not evenly spaced. Don't assume that these are evenly spaced. One thing I will also point out here is the magnitude of degrees. This is a 45 degree angle. This is a 21 degree angle. So we're dealing with some pretty large angles here. We didn't even project this onto a screen. If you project this onto a screen, you're going to have a pretty big diffraction pattern. If I go back to the diffraction pattern, that's going to spread pretty widely across the screen, especially if you're at 45 degree angle.